To solve this root equation, we can simply start by squaring both sides since we've already isolated one of the roots. On the left, we get x plus 23. Now on the right, we square the first term. 2 squared is 4. If you square the last term, the square root of x plus 3 squared is x plus 3. But then you get double the product of the middle terms. 2 times this square root is 2 square roots of x plus 3. So if we double it, we get 4 square root x plus 3. So we've canceled one of the square roots, but one still remains. Let's combine some like terms. So we get x plus 23 is equal to, and on the right we get 7 and an x, and then 4 square root of x plus 3, okay? I'm going to subtract x from both sides, but I'm also going to subtract 7. Okay, and when we do that, what we end up with is 16 is equal to 4, the square root of x plus 3. All right, so it's at this point where I can say, all right, I can cancel that 4 because it evenly goes into the other side. I get 4 is equal to the square root of x plus 3. This is nice because I can square both sides. I'm left with 16 is equal to x plus 3, and if I subtract 3, I get 13 is equal to x. Is this a solution to the original equation? It's a good question to consider. Let's check it. That's the square root of 13 plus 23. Is that equal to 2 plus the square root of 13 plus 3? Is this a true statement? Okay, so on the left, we get the square root of 36. On the right, we have 2 plus the square root of 16. Is 6 equal to 2 plus 4? It certainly is. 6 is equal to 6. That is true. And therefore, 13 is the only solution to the original equation. The goal is to solve an inequality using the graph of this particular function. So before we locate all the intercepts and asymptotes, I'm going to see if this thing factors. I believe it does. The numerator is going to be x minus 1 and x minus 4. The denominator is x minus 3 and x plus 2. Using these two equations, I can now answer part A. And what's the vertical asymptote? What about the x-intercepts? This is where both the denominator and numerator are equal to 0, respectively. So for the vertical asymptotes, the denominator is 0 if x is equal to negative 2, as well as if x is equal to 3. The x-intercepts are where the numerator is 0, and that is 1, 0, so 1 for x, but also 4 for x as well. So I would now like to figure out, well, what is the horizontal asymptote as well as the y-intercept? And this is where I'm going to use this version of the equation. The horizontal asymptote is going to be the ratio of the two numbers that are in front of the x squared terms, which is 1 over 1, or simply just 1. And the y-intercept, if I put 0 in place of every single x, I'm left with 4 over negative 6. That simplifies to a negative 2/3. But before starting to graph this thing, I'm going to answer the question of, does this function cross the horizontal asymptote, which is 1? I'm going to solve this by multiplying this to the other side of my equation. So that is changing this to solve x squared minus 5x plus 4, where is that equal to x squared minus x minus 6? This will definitely have a solution. The x squared terms cancel, but if I add x to both sides, on the left I would get negative 4x, and if I subtract 4 from both sides, I get negative 10 on the other side. So again, what I did there, maybe I'll put this step in. I added an x, negative 5x went to negative 4x, and I also subtracted 4. So negative 6 went to negative 10. If I divide both sides by negative 4, I get x is equal to, it'll be positive 10 fourths, 5 over 2. You can use a decimal. I think that's nice enough here. It's 2.5. I need that piece of information when I start to answer the question about the inequality. So with all this information, I now want to graph the function. So here's my grid. Vertical asymptotes at negative 2. As well as positive 3. Okay, so that's here. They're kind of close. We have x-intercepts at 1 for x and 4 for x. There's a y-intercept at negative 2/3, so roughly here. And there's also a horizontal asymptote of y is equal to 1. But I have this other piece of information. This is 2.5. This is where my function crosses over the horizontal asymptote. So the picture is going to be somewhat, compact here, but the thing I should see on my graphing calculator is a rational function that goes through these points, but then crosses over the horizontal asymptote at 2.5, and only at that spot. I know the graph also should increase through this point here and approach both asymptotes. And then the only other option is the graph is above y equals 1 over here. And always, there's only one spot where this graph crosses over the horizontal asymptote, and that's at x is equal to 2.5. So with all this information, I want to solve where is x squared minus 5x plus 4 divided by x squared minus x minus 6. Where is this less than or equal to 1? If I go to my graph, those y values are here and going towards positive infinity forever. This spot here, including that spot, and then over here. I don't want any portion of this graph because it's always strictly greater than 1. So the corresponding x values, I'm just going to write out what those are equal to. That's everything from negative 2 up to and including 2.5. So I'll put a bracket. And then I'll pick up at 3 and head towards positive infinity. And this is the answer to the question. For question 3, I'd like to analyze the graphs of the functions for f of x and g of x and find the inverse for the function if it happens to be 1-to-1. And I can see that if I look at g of x, which is the graph here on the right, this is definitely not a 1-to-1 function. I just found one horizontal line that goes through the graph twice. There's a lot of options, but it doesn't matter because this is not 1-to-1. Now, if I compare that to the graph on the left for the function f of x, which is equal to 1 over x plus 2, okay, this thing is definitely 1-to-1. Each horizontal line, even though the graph kind of looks like it might start to level off, it's still decreasing. No matter what, each horizontal line is only going through the graph once. So this is 1-to-1. Meaning it has an inverse. I'll take my equation, replace f of x with y, and note that the inverse is the equation that switches each x with a y and each y with an x. My goal is to now solve this equation for y, but again, I don't think that this is going to be too difficult. Just like in the previous review, I'll subtract 2 from both sides. I get x minus 2 is equal to 1 over y. And here I can cross multiply. I can multiply this y up here and this x minus 2 down here. You get y over 1 is equal to 1 over x minus 2, and you don't need that divided by 1 on the left. We get this as our equation. Here is f inverse of x. It is 1 divided by x minus 2. In question 4, we like to factor this polynomial by using the integer zeros and potentially some polynomial division. So question A is, can you find any integer zeros of this function? And that's not too hard. It appears that there's one at -5. There's one at 3. There's this one here. It's not at an integer. It looks like it's at a decimal. In fact, it even looks like it's at positive 0.5. And you could still use this value if you think that's correct. You can easily check all this in your graphing calculator. But to start with, I know -5 is a 0, but so is positive 3. For part B, this means that x plus 5 and x minus 3 are both factors, because if you put the zeros in place of x, they make the corresponding factor 0. If my goal is to completely factor the above polynomial, again, you could just try to guess the remaining factor, but if you're having trouble doing that, you could take this other approach as well, where you can use either one of these and divide it into the original expression. So I'm just going to go through that here. I'm going to choose x plus 5. You could have picked x minus 3, but both will work. So that's x plus 5 divided into 2x cubed plus 3x squared minus 32x plus 15. All right, let's see. I have to first multiply by 2x squared. That gives us 2x cubed plus 10x squared. And when I subtract these two things, I get a negative 7x squared minus 32x. I'm now going to multiply by negative 7x. I get a negative 7x squared minus 35x. And when I subtract this, that's a positive 35 minus 32, which is 3x. Okay, that's a good thing, because I can now multiply by 3 to give me 3x plus 15 with a remainder of 0. So I started with the equation 2x cubed plus 3x squared minus 32x plus 15. When I divided it by x plus 5, I got 2x squared minus 7x plus 3 left over. And I know that x minus 3 has to divide into 2x squared minus 7x plus 3, which leaves me with 2x minus 1 as the remaining factor. This is the answer to the question. And notice that here the factor is 0 at positive 1/2 or 0.5, and that matches up with what we have on our graph. I'm going to use the above formula to answer this question. The initial investment is given at $400. The annual interest rate is 12%, but this is compounded annually, so n is equal to 1. That makes the formula very easy. I'll change the percentage to this decimal, and I'm going to come up with my equation that b of t is equal to 400 times 1.12, because it's 12% added to 1, and this is raised to the power of t. It's nice. I didn't really have to divide or really worry about this exponent since both of those numbers were just 1. It took me to this. With this equation, I can now deal with part B, which is, what is the balance of this account after 8 years? So, what is B of 8? In my calculator, I'm going to enter my formula as 400 times 1.12 to the power of the variable in our calculator is x. Let's see what this is equal to. I'll get my answer directly from my table. Okay, 400, 1.12 to the power of x. I place in 8, And in 8 years, the balance of the account is $990.39. But a more interesting question is, how long is it going to take this account to double in value? And I can see that whatever my answer is, it's going to be less than 8 years. All right, so basically what we're doing is solving where is b of t equal to 800. That's double the value that we started with. So where is 400 times 1.12 to the t equal to 800? If I divide both sides by 400, again, no surprise here that you get 1.12 to the t is equal to 2. 2 because we doubled the other side. I'm going to leave some space in here because the goal is to solve for t by using logarithms. So I'm going to take the log of both sides. On the left, this t moves to the front of the function. Log of 1.12 is simply a number, and so is log of 2. T is equal to log of 2 divided by log of 1.12. Let's see what all that is equal to. Just type this into my calculator. 6.11 is my answer. Approximately, it goes on. And what this means is, in 6 years, you're going to be very close to double the amount that you started with. But since this is annual, you're only allowed to enter in years. Your account is not continuously growing. So for this reason, we'll say that, all right, you really have to wait 7 years until your account goes over $800. So 6 doesn't quite cut it. It's actually 7. All right, so down here is the function f of x. And I'd like to sketch these two separate transformations. I'll start with this one over here. Technically, there's really 3 changes happening. I'm really viewing it as 2 things, though. In terms of order of operation, we'd first work within the parentheses of this function. X plus 2 means the graph is, in fact, going to go left 2 places. And the second step is this multiplication by negative 0.5. I'm just going to do this in one step. The negative will flip the y value, and the 0.5 is going to cut it in half. But I mean, really, I'm just going to write down, we're going to multiply the y's by negative 0.5. I think that'll be good enough for what we're doing here. Let's see what happens. I'm going to start with this point. We're first going to go left 2. Now the y value is currently 8. If you take half of it, it goes to 4. If you make it negative, it goes to negative 4. So first, the negative reflects it down to negative 8, but then taking half of it goes to negative 4. This is the location of that point. Negative 8, negative 4. Okay, second, I have to deal with this point. It's first going to go left 2 places, and then multiply the y value, which is 0, by negative 0.5. It does not go anywhere. It stays right at 0, 0. And then lastly, we have this point. It goes over 1, 2. It becomes negative 2. Taking half of it goes to negative 1. This is our point. The entire graph should look like this. It is reflected over the x-axis. It has been compressed because we divide each y value by 2, but it also moved left 2 places. To complete this, let's look at this other equation. There's 2 differences. I see we're first going to deal with this 2x. Just like over here, adding actually meant to go left 2 instead of right 2. Here, if you're multiplying the x by 2, the net result is going to be to divide each x value by 2. So we're going to divide the x's by 2. The The last thing is this plus 3, which means go up 3 places. Let's start with this point. The x value is at -6. You take half of it, it's going to go to -3. If you then go up 3 places, you go up to 11. So that's -3, 11. Okay? For this point here, I'm going to take half of the x value. The x value is 2. You take half of it, it's now at 1. If you add 3 to it, it goes up to 3. 1 comma 3. My last point is here. The x value is 4. If you take half of it, it goes to 2. If you then add 3 to this spot, you go up to 5. And this is my graph.